Okay, so we're going to talk about applications of our exponential functions here. This is where you will use these things in real life. It is truly applicable to things that you are seeing in real life as well. So, all right, so growth and decay is where we're going to really see exponential functions being used, right? Growth in your community or population, growth in animal population, decay in medicine, and things like that. So any quantity that grows or decays by a fixed percent or regular intervals is said to have an exponential growth or decay. The formula is there, A equals P times 1 plus or minus R T, where A is going to stand um, for your future amounts that you're trying to get to. P is going to be your initial value. R is the rate. T is the time. Um, if it is a growth, we're going to use the plus rather than the minus. And if it's a decay, we're going to be using a minus there for our rate. These formulas will be given to you, so don't feel like you need to memorize them. Here we're going to determine whether or not these represent growth or decay. Okay, so if we look here, right, we've got a minus, so that makes this a decay. Okay, we've got another minus, so decay. Notice this number is greater than 1, which means we've added something to it, so this is a growth. We've got 0.25 there, right? And this is a positive number, so this is a growth. If it was negative, it would be a decay. Okay, and here we've got a negative, so that would be a decay problem. Okay. So here is our first example for what this might be, right? The approximate number of fruit flies in an experimental population after T hours is given. So 20e to the 0.03 T. Does this represent a growth or a decay? This would be a growth, right? Because our number is positive there, so we're choosing growth. The initial value of fruit flies in this population, right, is the number being multiplied, so it's 20 fruit flies. Okay. And they want to know how large the population of fruit flies is after 48 hours. So we're just going to take the 48 and we're going to plug it in as our time. Let me scoot down here. So we've got, let me use blue instead so you can see it. 20e to the 0.03 t, where our t is 48. Okay, we get 84.4. Now let's talk about that. Can you have 84.4 fruit flies? The answer is no. You can't have part of a fruit fly. Maybe your fruit fly lost a leg or something, but you really can't have part of a fruit fly, right? They're whole flies. So we need to round this number actually. How large is the population? So we would only have really 84 fruit flies at that time, right? We haven't gotten to 85 yet. So we'd only have 84 fruit flies in 48 hours. All right, so here we have doctors prescribed medicine. They must consider how much the drug's effectiveness decreases as time passes. So an adult takes 40 milligrams of ibuprofen, so that's what we're starting with. Each hour, the amount of ibuprofen in the person's system decreases. So decreases, we're going to be using a minus, about 29%. Now remember, we need to write the percent as a decimal, so that's 0.29 there for the rate. And how much is left after 6 hours? 6 hours would be our time there. This is telling us that it's a decay. The decrease status. This was our initial value. Okay, so we just gonna write our equation, right? And remember our equation is P times 1 plus or minus the rate to the t. So our initial value was 400. And then we've got 1 minus our rate, which is 0.29, to our time of 6 hours. Okay, and then here we would just type this into our calculators to get our answer out. We're going to get 51.2. Again, the formulas are going to be given to you. You do not have to memorize them. All right, so we've got the equation here for the population growth of bacteria. Um, the variable A represents the amount of bacteria after time measured in hours. So we're going to answer the following questions with a colony of 500. So remember, 500 is going to be that P up there. So we've got 500 e to the 0.107 t as our equation. So how many bacteria are represented after 10 hours? We're just going to take that and plug 10 hours in. So 500 e to the 0.107 times 10. And your calculator will do the work for you. E is a button on your calculator. So you just find that button there and click it. It is right under the log and above the LN. It's the blue there, so you'd hit second LN to get it. And we'll get that there are 1,457.6895. So after 10 hours, how many really did we only have? Right, we would stop at the whole number. So really 14,000 or 1,400, right? 57 is what we would stop at. Okay, the second question we got there is how many bacteria are present after 2 days. Now, 2 days, we're going to have to convert to hours. Remember, there are 24 hours in a day. So in 2 days, there would be 48 hours. Okay, and we're just going to put 48 into that equation. So 500 e to the 0.107 times 48. We're going to get 85017.58. Okay, so it's a really big number again. So we got 85,000 there. But again, we're going to round to the whole number. So that's 85,017. Okay. C. How long does it take for the colony to triple in size? So here, we're no longer solving with a time. We need to find the value of time. So we're going to set this equal to what it would be triple in size. So 500 times 3 gives us 1,500. So we need to solve for that. Equals 500 e to the 0.107 t, right? So we're going to divide both sides by 500. We get 3 equals e to the 0.107 t. Now remember, we've been working on solving exponentials and logs. So to get rid of something, e, we're going to put ln in front. So we got ln of 3 equals ln of e to the 0.107 t. And we're going to cancel out the e and ln. So we've got ln of 3 equals 0.107 t, and then divide by 0.107. And then this is where you'd go to your calculator and type it in, and we would get t to be 10.3 hours. Okay. And the next ones we're going to talk about are going to be interest and how that works, which is going to be very useful for you. There are lots of different formulas here. Again, you do not have to have them memorized. You just need to know when to use the formula. So we've got compound interest yearly, which looks just like the growth and decay formula, except that you're always increasing because you're increasing on your interest. Then we've got compound interest. Okay, and this is how used when you're doing things maybe monthly, bi-monthly, quarterly, things like that. That's when you use compound interest. Continuous interest, okay, is when it's constantly going to be the same. Now the pieces there that are going to represent, we've got P that stands for the initial investment or the principal amount that you've put in. Okay, the rate is just like the rate of the bacteria and things growing on the other problems we did with the growth and decay. Time is how long you're going to keep that. And then the N is that compounding period. So like for the compound interest yearly, right, we don't have an N because we're dividing by 1. So you can always use the compound interest formula there. So like you can have things like monthly, quarterly, biannually, daily, things like that are compounding for your periods. Again, your formulas will be given to you. Now the key for these is you have to be able to convert some things, right? So if we're talking percentages, we got to convert to decimals. Remember decimals, we just moved the decimal over 2 places. So 11% would really be 0.11, 7% is 0.07, 3.75 is 0.0375. 1.275 is 0 or 0.01275, and 4.8 is 0.048 as a decimal. Okay. I really see this a lot. We always forget to convert, so please remember to convert your percentages to decimals. Converting months to years, okay, because a lot of times we do things yearly rather than monthly. So 9 months is going to be 3/4 of a year. 18 months is 1 year and a half. Okay, 30 months is 2.5 years. 3 years and 6 months is 3.5 years, right? And 2 years and 3 months is 2.25. Okay, you just got to be able to switch between those. And then the compounding periods, this one is also really important. I would star, highlight, circle, underline, do whatever you got to do to make sure you remember these. Annually or yearly is one year, right? Biannually means you're doing it twice a year. Quarterly means you're doing it 4 times a year. Monthly means 12. Daily is going to be 365. And weekly is going to be 52 because there's 52 weeks in a year. Okay. So let's look at our first problem here. Suppose your grandparents invested $12,000 into account, right? So that's our initial investment. That's our P. And an account paying 5%. I'm going to write this. This is going to be our rate, and it's actually equal to 0.055. So keep that in mind. Compounded quarterly. Okay, so our N value is 4 when you were born. The money is to be given to you on your 18th birthday. How much will be in your account when you turn 18? So our time is 18. So we've got all of our pieces here. We just got to plug it in. We're going to be using our compound interest formula because we're asked how much. We're asked how much will be in the account when I turn 18. So I've got P equals 1 plus R over N to the NT. And I've just got to plug in. So my initial value was 12,000 times 1 plus my rate, which was 0.055, over my compound, which I'm compounding quarterly, so that's a 4. That is 4 times 18. Okay, and then we just type this into our calculators. That is an 18. I know it doesn't really look like an 18, but that's what it is. Type that into your calculator just the way you see it, right? The calculator will do the fraction and everything for you, and it'll pop out, and we're actually going to get 32,000 and $77.73. With money, we round to the hundreds place, right? Because we got pennies. So make sure you're doing that. Okay, the second question here says how much would you have had if it was compounded monthly? So we're changing just one part of that problem, right? We're changing our 4 from a 4 to a 12. So we're going to have $12,000. 1 plus 0.055 because the rate didn't change, but we're doing it monthly, so that changed. So 12 times 18. Okay, and so there we're going to get 32,221 and 85 cents. But that's not what they asked. They asked how much more. So I'm going to take that and I'm going to subtract the original price that we had. Okay, and we would have made $144.12 more. Okay. And the last question here, if the same amount was invested in the account that was compounded continuously, how much would we have received? So we're changing it. We still started out with our initial value of 12,000, but now we're doing E because we're doing compound continuous interest. So E to the rate, and our rate was 0.055 times our time, which is 18, right? Because this is PE to the RT is for continuous, okay? So when we solve that out, we're going to get 32,294 and 81 cents. So compounding continuously would have been the best rate to go. Most banks don't give you that option. So make sure you do the math to figure out where you're going to get the most money out of it. Okay, here's another example, right? You've invested $1,500 in an account, giving you 3% interest compounded quarterly. Okay, so this was our initial investment. 3% was our rate, so that's 0.03. Compounded quarterly, so N is 4. How long will it take to investment to reach $5,000? So we're looking for T. T is our question mark. Okay, so if we're compounding quarterly, remember we're using P1 plus the rate over the compound into the time. Okay, so we know that we want to make $5,000, and our initial was 1,500. 1 plus our rate is 3% over quarterly, which is 4 to the T. Okay, so what's happening first is we're actually multiplying by this 1,500, so we're going to divide by that first. Okay, and when we do that, I'm going to leave the fraction because it gives you a decimal. Okay, so that's 10 thirds equals 1 plus 0.03 over 4t. Okay. Now we need to take the log of whatever that nasty base is. Now you could type that in, you could get a decimal and use that, but it's not going to be exact. I like to keep things exact. So I'm actually going to take log base of that whole thing and type it straight into my calculator. Remember, we get to log base by hitting math and scrolling down to log base, okay? of 10 thirds equals our 4t, and then we divide each by 4. So then this is what we type into our calculator to get our answer. It looks nasty, but your calculator does it all for you, so do not stress. You just have to type it in the exact way that you see it, and you'll find that your t ends up being 40 years, 0.3 years. Is how long it'll take us to get there, which is a very long time, right? 3% is not a good rate. Okay, this last one I want you to try to answer for yourself and see if the answers that you get match what I have on the board for you. Okay, so you should have found that it was a decreasing, right? Because 0.82 is less than 1. The initial value was 20,000. Finding it after 5 years, right? You just create your formula and then plug in 5. So you should have gotten 7,414 and 80 cents. And the last one was definitely the toughest one there. You were solving for the time, right? So we would have divided by that 20,000. And then taken the log of the 0.82 times of the 0.25 and found that it was approximately 7 years. For that car to reach. And this happens a lot in real life. Cars do depreciate really quickly, especially as soon as you put miles on it. So it's also something to keep in mind as you're going out there searching for cars. If you have any further questions, please make sure you just write in the margins of your notes and just let me know when I'm back.